Yeah,
I don't
sure.
know who's going to be traipsing in.
Okay, wait a little longer.
Well, I think we just better go. You'll be patient with us.
Oh yeah, sure, that's fine. We can go anytime. Yeah,
It's not like Michigan where everybody knows to come in.
I'm good. Anything's fine.
Well, okay, folks, I know we'll be having people traipsing in as the morning goes on, but I think we should get started so we don't run out of time on the other side. It's my great pleasure to introduce Professor Tony Bloch, University of Michigan, the once and present chairman
That's true.
of the math department. Two terms.
This is the second term.
Really unusual, cruel and unusual punishment. Anyway, Tony is distinguished in many different ways. He's a number of very high-profile positions. He's chief of SIAM J, control optimization, and he's editor, associate editors on many similar journals. He's fellow of these increasingly rarefied settings, IEEE, okay, he's a SIAM Fellow, but he's also a Fellow of the American Mathematical Society, which is this is a pretty rare. The oxygen is pretty thin. He's had many distinguished fellowships, Guggenheim Fellowship, SIAM Fellowship. If you're familiar with those, you'll know how competitive these fellowships are. My association with Tony is, when we were young, I watched as Tony emerged with another maybe 24 people from one of the most distinguished laboratories in control at that time. I think many people who looked to mathematics for insight into control at that point became somewhat bewildered or overwhelmed and either did very, very sterile things, and control took a kind of sterile turn, whilst other people became, became unenamored. Tony's work the content of his work, and particularly the style of his work, has had tremendous impact on me in my career, because he's been able to simultaneously work on extremely practical and important engineering important problems, whilst really functioning as a mathematician, not having to choose one or the other, but both at the same time. Very, very, very rare that we see this in the field. And so I've learned a lot from Tony over the years, and I hope you'll learn something from Tony this morning. So thank you so much.
Well, thank you, Dan. So likewise, I've learned lots from Dan, and it's a real pleasure to be here at Penn. So I've known Dan for many years and seen lots of interesting robots doing different things. And of course, it's been a pleasure to see also how not only Dan has developed, but also how these robots have developed over the years. It was fun just recently to see Jeff's robot with a flexible back moving around. So It's kind of fun to be here. So I should say, you know, I'm not a roboticist, as Dan said. I'm more of a mathematician, but I do things in robotics and control and physics in general. So I hope I can say some things that will be of interest to you. So I'm entitled to talk periodic orbits and hybrid robotic and biological systems. So I've been interested in recently, actually, in the existence of periodic orbits in all these different spheres, and I wanted to try and tie them together a little bit today. So, of course, periodic orbits are very important in locomotion, for example, in robotics. They also play a huge role in biological systems. You know, we all have circadian rhythms. Each cell has its own cycle. And I've been doing some work at Michigan recently with a mathematical biologist called Indika Rajapakse on the evolution of stem cells and controlling those. So I'm not going to say much about that today, but that's also a little bit of the background of some of my interest in these systems that are biological, that have periodic behavior. So one of the things that I have been interested in for many years is nonholonomic systems. So those are systems with constraints, and particularly non-integrable constraints. So they're generalizations of Hamiltonian, classical mechanical systems, which can have either dissipative or periodic behavior or lots in between. So I want to say something about those and how periodic behavior arises in these systems, and in particular, how discrete symmetries play a role in these systems. So the other topics that I've listed here, hybrid and symmetric hybrid systems, this arises from some work that I did with a student, Hamid Razavi, who was joined with me and Jesse Grizzle, who I'm sure many of you know, who's a roboticist at Michigan. And there, again, discrete symmetries play a role in locomotion in these systems. And I want to say something about how those arise. And then I'm going to sort of link it a little bit more closely with non-holonomic systems. I've been looking more recently with a student I have called William Clark, where we've been looking at generalizing the classic billiard problem. So the famous billiard problem is if you have, you know, people call it the billiard problem, but really it's just a particle bouncing around in some sort of enclosed area. So we wonder what it would look like if you had a real system bouncing around, in particular a rolling penny or a billiard ball. So interesting things happen there. And then I'll link to some work, if I have time, on biological systems with Matt Kvalheim. So this was motivated by the various biological things that I was looking at earlier, but in particular we were looking at some synthetic biological systems. There's the famous repressolator, which is a kind of synthetic oscillator which oscillates in a stable manner. And again, we were interested in proving the existence of periodic orbits in that system and other systems of that type. So I'm going to begin by saying something about non-holonomic systems. So I'm sure many of you know about these, but I'm going to show basically a little bit about it and say something about some of the basic examples. The example I always like to show is the vertical disk, which is simply a disk, or if you think of it as a coin that can't fall over. I'll come back to the falling over one in a moment. Of course, in general, it can fall over, but it's great for just illustrating some key ideas in motion and control. So the idea is I just have this vertical disk moving around on the plane, R2. Two other parameters are the two angles. It can rotate around the vertical, and it can also steer itself. So basically it can spin and it can steer. And it's a very nice example for thinking about control and constraint dynamics in general. It has a very simple Lagrangian. So if you didn't have the constraints, it looks like just a bunch of free particle Hamiltonians or Lagrangians put together. So the kinetic energy of moving around in space and spinning around. And so I and J here are the moments of inertia. And it has these two constraints, x dot equals r cosine theta phi dot, and y dot equals r sine phi theta dot, which just constrain how you move around in the xy plane. So basically you can see where they come from. If I just rotate the penny, it moves along, say, this diagonal line, and because of the constraint on the motion that it has to roll, that tells you how you move in the x and y directions. And the important thing is it's a constraint on the kind of motion you can get, but not on where you can move. And that's key to controllability in some sense. The other point, why is it non-holonomic? These constraints are non-integrable. I can't rewrite them in terms of the configuration variables only. I can't rewrite it in terms of x and theta. They're constraints on the velocities. So it doesn't constrain where you move around in the configuration space. So those are typical non-holonomic constraints, and you see them in rolling, and skating, and cutting, and so on. So what is the dynamics of the system? Well, if I think of it as a controlled system, the natural controls are the controls, if you're thinking of sort of steering the wheel around or steering a car, the controls are sort of rotating the wheel and turning it. So those are the two controls. So you have the intrinsic dynamics, which comes from the Lagrangian. And on top of that, you have controls, U1 and U2, which are steering and rotation. And you enforce the constraints. And this is the famous Lagrange-D'Alembert equations. So you can work it out, what they are. So you have these two vector fields which enforce the constraints. And those are appended by Lagrange multipliers, lambda 1 and lambda 2. And you have these controls which tell you where you can move. And one can think about various problems, but in particular, you can think about moving this around, and in particular, the problem of controllability. So can you move it around anywhere in the configuration space? That's the basic control problem. So, so the way we think about it, so the controls U1 and U2, we call the controlled variables or the base variables. That comes a little bit from the geometry of the system. The variables X and Y are called the fiber variables because sort of mathematically there's a sort of fiber bundle structure associated with the system. So you think of the base of the system in geometric languages where you can directly control it, and the fiber is where you'd like it to be controlled. And the whole point here is that you can control directly your steering and rotation, but the whole system is controllable in the space. So it's just like when you're driving a car, you put your foot on the accelerator, you can turn the wheel, but you know you can move your car anywhere you like. For example, if you want to move it into a parking space, that seems like a tough problem, and when you first do it, it is a tough problem, but we all in the end learn how to do it, right? We know by turning the wheel back and forth and going forward, reverse, eventually we can get into the parking space. And that's the basic control problem in this case. And the whole point here is that the base variables are directly controllable, your steering and acceleration. But in fact, because of these constraints, you might think constraints are a bad thing. In fact, constraints are a good thing in this case. They link the fiber variables, x, y, to the variables theta and phi, and you can move anywhere you want. So it's a controlled system. And you can show that sort of theoretically in control. For those of you who know, if you take the Lie brackets of the control vector fields and the drift vector field in this case, you can show that the vector fields span the space in a suitable way. So this is a dynamic problem. I also want to contrast it with kinematic, which is often used in robotics. So in the kinematic problem, you have direct control over the velocities rather than the forces. And in that case, the most general first-order system satisfying the constraints is the system that you want to look at. So we call it a constraint distribution. You enforce the constraints, and you just look at the possible vector fields which satisfy those constraints, and you end up with this first-order system that I write at the bottom here, q dot equals u1 x1 bar, u2 x2 bar. And these are these two vector fields, and that is just the system that you get without any dynamics. If you just sort of put your hand on top of the wheel, for example, and you were just steering it around. You can think of it also as if you had a rolling ball, for example. If you put your hand on top of the ball and you want to see where you can move it around. That's the kinematic system. And another sort of famous system, I won't say too much about this, is the so-called non-holonomic integrator, made famous originally by Roger Brockett. And one of the nice things about these systems is that they're usually controllable just by one order of brackets. You take one set of brackets, you sort of move it around in XY space, you take another bracket, and that'll give you the motion. And one of the nice things about these systems is that periodic inputs often leads to translation. So one way of controlling these systems actually is you put in sort of periodic inputs, and that leads to translation, for example, in the XY plane. And that's pretty similar in a way to what happens in locomotion. And I want to come back to that later a little bit. So often you sort of have some sort of periodic behavior. You're moving your legs back and forth, and you translate. Similarly, here you have periodic behavior, for example, in your theta and phi variables, and you get translation in XY space. So I would say there's some natural similarity, if you like, between these smooth non-holonomic systems and systems with impacts, like robots. And in fact, if you look at the literature on systems with constraints, often people generalize it from smooth constraints to systems with impacts. You can think of a system with an impact as having a one-sided constraint, right? You move around, you hit the floor, and you can't go through the floor. So there is a similarity in these systems. So let me just say something a little bit about the dynamics of these systems. So more generally, so that's the example you should keep in mind more generally, you can think of just having two sets of variables. You know, one set is related to the other set by the constraints. So I like to call them S and R. So in the general picture that you have here, you can think of the R variables as, say, the theta and phi, those variables you directly control for steering around, and the S variables are these fiber variables. That's where you'd like to be able to move as well. So that's the general sort of set of constraints. And how do you find the equations of motion for a system? Well, it's the Lagrange-D'Alembert equations. That means you take variations of the Lagrangian. If you had no constraints, you just have Lagrange's equations, and you'd end up, you know, d by dt, dl dq dot equals dl dq. If you have constraints, you have to choose the variations when you do this variational problem to satisfy the constraints. And the idea is that you sort of supplement the variational problem by the fact that the curves satisfy the constraints, and you take variations before imposing the constraints. That's the key idea. So it's a little bit different from what we normally do in sort of elementary calculus, right? If you're doing a constrained variational problem in calculus, you append the constraints to the Lagrangian, right? You have L plus lambda 1 times the first constraint plus the second constraint. That gives you a variational problem, which is not what we're doing here. And it's not consistent with the Lagrange-D'Alembert equations or indeed with Newton's laws. So just to write that out, so if I take the variation, I get the standard Lagrange's equations, which we all know, and then we enforce the constraints as well, and we get a slightly modified set of Lagrange's equations combined with these constraint equations. So that's the basic set of non-holonomically constrained systems. And one of the nice things about it is you can sort of, just to see the geometry of the system, you can convert the Lagrangian into constrained Lagrangian, which simply means solving for the variables in the Lagrangian in terms of the constraints. And then I get this rather elegant system here, the second equation from the bottom, which encodes the Lagrangian equations plus the constraints on the left-hand side. And there turns out to be an extra term on the right-hand side, which is actually a curvature term in mathematics. So it's a mathematical curvature, and it's really measuring the curvature of the non-holonomic constraints. It's measuring how non-holonomic things are. So if you had holonomic constraints, in other words, constraints on the configuration variables, this term would vanish. So this measures how much the system is a non-holonomic system as opposed to a system where you've just constrained it, say, to move on a surface. So those are the variables. I mean, it's not, you know, the details don't matter, but it's kind of a nice thing. And this set of equations actually has a very nice history. And the beautiful thing about them is these equations are essentially equivalent to Newton's laws. So if you wanted to formulate the equations just as a balance of forces problem, which is F equals ma, this is the set of equations you would come up with. And there's always been a bit of confusion in the non-holonomic literature about this, you know, because you can think of it either as a variational problem, which mathematicians love to do, or as a balance of forces problem, which engineers like to do more. So this is kind of a modified variational principle, which I just showed you, which is consistent with Newton's laws, F equals ma, which is the primary thing here in classical mechanics, and it gives you the right thing. And the key idea here, as I said, is you do these variations, and then you impose the constraints, and it gives you the right set of equations of motion. If you just if you appended the constraints to the Lagrangian originally, you'd get a different set of equations, which sometimes people call vaconomic, which will give you a somewhat different set of dynamics, which I'm not going to worry about too much here. So you can extend this. So this works for the penny. I can get the dynamics. I can look at the controllability. You can get all sorts of more complicated systems. So for example, I could allow the penny to fall, of course, as it naturally would. And of course, it has a richer dynamics if it falls. It can oscillate back and forth. But in fact, the dynamics is rather beautiful. You know, if you just take a coin and you roll it along the floor here, which I could try and do, but I guess I won't for the moment, you could roll it along and you'll see it moves around stably. You've seen this, right? It'll move in a curve and it'll oscillate back and forth a little bit. So you get, basically you get periodic, you get sort of motion along the floor as it rolls, and it oscillates a little back and forth. So it's stable, but not asymptotically stable in the way it moves. So it sort of oscillates a little bit about a sort of relative equilibrium. So here's another nice system that I like to think about. So as I said, I want to get to periodic motion, and I want to compare periodic to dissipative. One of my favorite non-holonomic systems, which illustrates this, is called the Chaplygin-Sleigh. That's actually, it's a very simple system. You can think of a triangular table. That's the way you should think about it. So you can think of a triangle, or think of it as a table with two legs, which are ordinary legs, and you replace the third leg by an ice skate. That's it. Something that's very similar, which you see in real life, is a trolley, for example, that you might use in a supermarket. So we have, say, two fixed wheels. You can think of that as the stable legs, and the two wheels that move back and forth. It behaves very similar to this. Anyway, this has rather interesting dynamics, just like a trolley. So if you tried pushing a supermarket trolley around it, normally, of course, we walk around sort of like this, holding it, but you could try and give it a push, right? And if you ever tried doing that, if you let it go, you notice it'll often swing around, right? It only likes to move in one direction and not the other direction. And this is true, in fact, for the chapter sleigh. It likes to move in such a way that the center of mass is ahead of the blade. So it has that kind of interesting behavior, which I'll illustrate in a second. So you can write down the equations of motion. These are the reduced equations of motion. And the variables here, v and omega, that I've written here, are v is just the motion, sort of along the direction. So the key thing here is the center of mass and the contact point of the blade. So the things to think about here are the velocity along the line between the contact point of the blade and the center of mass, that's v, and then I can think of rotational motion, omega, say about the center of mass. So these are these two variables, so it's a very simple set of equations of motion, and but it's a rather beautiful thing, and if you linearize it, you'll see that you get, in general, if you linearize about the equilibrium, you find you get one zero eigenvalue and one non-zero eigenvalue, which, if you know something about Hamiltonian mechanics, you know is not consistent with a Hamiltonian system. In a Hamiltonian system, the eigenvalues are either along the imaginary axis, in which case it's stable, which is like this penny as it oscillates and forth, or the eigenvalues are sort of equally distributive. There's one on the left, there's one on the right. That's what happens in a Hamiltonian or Lagrangian system. Here, you don't need to have that symmetry. In fact, in this case, if you linearize about the stable direction, you get one zero eigenvalue and one negative eigenvalue, and that might indicate there's a chance for stability. It's not quite enough for stability, since it's a nonlinear system, but in fact, you can check it's stable. And the sort of phase portrait looks a bit like this. So there are a bunch of arrows. So in fact, those arrows show you that you approach motion in one direction. You'll go along in the stable direction. So if you start it in the stable direction, like the supermarket trolley, you'll continue stable. If you start it in the other direction, it'll swing around and go to that stable direction. So that's what those arrows tell you. So it looks a bit like a phase portrait for the harmonic oscillator, except that the arrows sort of go like this. They meet in the middle instead of going round and round and round, as you have for a harmonic oscillator. So that's how it behaves. It's kind of a fun thing, and there are other interesting systems that behave like that as well. But in any case, this doesn't oscillate. I want to show you something that does oscillate. So to get to oscillations, so I'm going to come to another set of equations here, which are called the Euler-Poincare-Suslov equations. This is also a nicely constrained system, so I'm sure many of you will recognize the system here is just the equations of motion for the rigid bodies. If I take a rigid body, that's Euler's equations, right? I have I omega dot equals I omega cross omega. And you might think about what sort of interesting constraints you can put here. Well, the simplest one is a linear constraint. A dot omega is equal to 0. And the physics of that actually is if I take a rigid body and I stick a rigid rod through it and put it inside a sphere with sort of blades on the end, it sort of constrains how it can move in one direction. It'll stop you. So this is a constraint on the velocities, all right? It says, for example, I can't rotate perpendicular to the blades. So it's a constraint on how you can oscillate. So that's a particular kind of system. It's actually easy to solve quite explicitly. Again, you just append the constraint by a Lagrange multiplier. You can solve for lambda. And you can check that, in fact, that if this is a rather interesting fact, which I won't try and prove here, that if A, which is the vector that imposes this constraint, if A is an eigenvector of the moment of inertia tensor, I just take the inertia tensor as a matrix, I look at its eigenvectors, then you can show it's measure preserving, and it oscillates rather like the penny. So you get oscillatory behavior. If A is not an eigenvector, you get dissipative behavior. So this is an interesting case where it can either be oscillatory or dissipative. So, and in fact, even with by the way, coming back to my Chaplik and Sleigh, if the center of mass is above the blade, then it also behaves a bit like the penny. So it really needs that little displacement of the center of mass from the blade to behave in this asymptotic way. So this is sort of a generalization of that. And both these problems sort of generalize. You can get a very nice class of mathematical systems which generalize these systems called the Euler-Poincare-Suslov equations. And these go back a while. So the Chaplygin scale goes back to Mr. Chaplygin. So a lot of the people in this area are Russian, by the way, for whatever reason. So Chaplygin in 1895, Suslov in 1902. So that's where those go back to. And you can write down these equations in general. So these are the Euler-Poincare-Suslov equations that I've shown here, equations 2. And you can write down very specific conditions for when it's oscillatory or not oscillatory, if you have an invariant measure or not. So I won't worry too much about the details, but you can actually do that. So I just want to illustrate it with an example. So this condition, by the way, of A being an eigenvector is generalized by this equation 4 here. So this is really the same thing. It's whether or not. So depending on how the constraints interact with the dynamics is the way to think about it. It's either oscillatory or it's not oscillatory. So here's a case. So we wondered about this, and we came up with a rather interesting example, which is illustrative of what I want to show here, discrete symmetries and oscillations. So here's a rather fun system to think about. So as I said, the important point for this sort of Suslov problem, or Chaplygin slays, is the displacement of the center of mass from the contact point of the blade. So you could try and do something that is a little richer than that and combines these two, the idea whether the contact point is above, at least whether the center of mass is above the contact point or not. So I just put a little oscillator on the Chaplygin sleigh. So I think of the sleigh as being zero mass, it has a skate on it, and I have an oscillator which moves back and forth above the contact point, and you could ask what the dynamics looks like. And it turns out to be rather rich and beautiful and illustrates some periodic dynamics. So let me just show you that. So there's the sleigh, the mass slides around along the direction of the blade, and the mass is coupled to the sleigh through a spring. So just think of my mass oscillating back and forth on the sleigh with a spring, and you might wonder, how does this behave? So we weren't sure when we started with this, but anyway, so you can write down the Lagrangian. So here it is. It's a little more complicated than the one for the sleigh, but the details don't really matter too much. And this is what the reduced dynamics turns out to look like. So this generalizes the dynamics that I showed you earlier. It has so these two equations at the bottom here are similar to the sleigh equations, which had that sort of zero eigenvalue and negative eigenvalue. And then I have a sort of oscillator equation. So if you think about it, it's a rather nice set of equations. I don't want to worry too much about it during the talk, but if you look about it, the first equation is really like the harmonic oscillator. If you think of R double dot equals minus KR, that's just the oscillator, right? X double dot plus KX equal to 0. The first equation you see in an ODE class, if you like, first, second order equation. And these are the sleigh equations. And anyway, you can look at the dynamics. And what you notice, actually, is there's a lot of symmetry in these equations. And I'll come back to this for hybrid dynamics in a moment. So if I look at these equations, you note they're invariant under a lot of little discrete translations. So first of all, there's a relative equilibrium at a given point. But if I look at the, so R equals 0 and P equals P0, that's similar to the sleigh sliding dynamics. But you can note in particular that the equations are invariant under these 4 transformations that I show at the bottom. If I just reflect things around, P1 to minus P1 and so on. And I can use that actually to integrate the system. So you can actually study this, you can study the dynamics. You can show, for example, that R of minus T is equal to minus R of T. And you can check that if you use this dynamics in a nice way, you can check that R of T just satisfies this harmonic oscillator equation, this first equation on the board here, and you get periodic solutions. And in fact, you can sort of, and then using the rest of the symmetries, you can take these periodic solutions in the R variable and show that induces periodic behavior in the base variables as well, in the P1 and P2 variables in translation. So I'm not going to worry too much about the details here in the interest of time and so on, but you can work out that you get very nice invariant dynamics, and let me just show that to you. So this is one of the trajectories of the dynamics. You get this reduced dynamics. And in fact, you can show that generic trajectories of the system are quasi-periodic motions on 2-dimensional invariant tori. So basically, it's 2 sets of periodic motion in the variables P1 and P2 and R1. And the trajectories of the contact point are rather beautiful. So this is the trajectories of the contact point. So if you think of the contact point of the sleigh, you get these rather beautiful patterns. So it's a little quaint now, but I don't know if you, as a child, you know, we always used to have, maybe some people still do, there's a thing called a spirograph. You remember the spirograph? You had these wheels, and you take another wheel, you put your pen in it, and you go around these wheels, you can draw these beautiful patterns. Anyway, you get these rather beautiful spirographic patterns. And you can see they are periodic, but they've got this very rich dynamics as well. So it's a very simple system. It's just a sleigh with an interior sort of oscillation, if you like, but it gives rise to this very rich periodic dynamics. And you can show there are other non-holonomic systems which behave in a similar integrable way. So I could say more, but what I wanted to do is get onto hybrid dynamics. So this was all smooth, but periodic behavior, and I want to sort of link it now to hybrid things and robotic type things. So this relates to some work, and it's much closer to the work of Dan in the lab here on stability of hybrid systems and locomotion. And what I want to show again somehow is that symmetry, the same kind of discrete symmetries lead to stable locomotion. So, so as I say here, stability in legged motion, you can characterize as either static or dynamic. So I'm sure many of you here know this better than I do. You can think of either your robot as being statically stable, sitting over its base point and not falling over, or you can have some sort of dynamic motion, the locomotion, that's also stable. And what we're sort of interested basically in is the stability of this dynamic locomotion. So, so how does one model stable dynamic walking? Well, again, you're interested in periodic behavior, right? Basically, you're moving your legs back and forth, and you want the system to behave in a nice way. But as I mentioned earlier, really, you want that kind of periodic motion to lead to something good, right? So you'd like to be able to get from point A to point B, or move in a circle, or whatever you want to do. So the idea is you model the walking gaits as stable periodic orbits of the dynamical system. And, of course, it's an approximation, but of course, as I go back to the work of Dan, you want these approximations, So I always remember Dan talking about pogo sticks. Pogo sticks are a wonderful example of this, right? And the pogo stick is not too different if you think about it from what I just talked about. It's a rigid body with a spring. The only real difference from what I just talked about is that it hits the ground, right? And then you want to see what happens, and you'd like to maybe get some periodic motion. This is a natural thing. How does one study periodic motion? Well, often the idea is to look at a Poincare map, right? So I'm sure most of you are familiar with this. The idea is basically you look at the dynamics. So if it's periodic, you look at it hitting some sort of surface of section, which I'll come back to in a little bit, and you look at the eigenvalues of the map, which takes you from the surface of section to another surface, to the surface again, and you look whether that behaves stable. So that's the basic idea. And the problem with this, and again, I remember many conversations with Dan about this, is often it's very complicated to compute this, right? If the system is integrable in the ways I've just discussed, for example, you hit the surface of section, it's a nice simple system, just like maybe a planar rigid body, you can compute it exactly. Very often, of course, if it's a complicated robot with various interconnections, right, just computing it is really tough, right? Even if it has 2 or 3 links, it's not integrable. Even when it's floating in space, you have to compute it numerically, and coming up with the periodic orbits is a tough thing. So what we did in this work here is we tried to sort of simplify it by looking at what are called these symmetric hybrid systems, where we impose the simple kind of symmetry, and that gives rise to sort of stable periodic motion with nice Poincare maps, which behave nicely. And in fact, the example I'll show you is kind of simple, but it generalizes to quite complicated things. And then in addition, of course, in addition to actual stability, you'd like asymptotic stability, you can do that a little bit by breaking the symmetry. So let me explain a little bit how this happens. It's a little bit, in a way, it's related to this, the original work of Raybert and Kodacek for planar walking. The idea here is to extend it to 3D legged locomotion and to sort of derive symmetry, at least to derive stability in some sense, by imposing these discrete symmetries. So I want to illustrate it by a simple example again. So rather like the pogo stick, I want to look at this so-called 3D linear inverted pendulum, which people call the lip. And so it's a very simple system, but it sort of illustrates the key symmetries. But the beautiful thing about the work that Hamid did and so on, and together with Jesse's lab, and also Hamid eventually moved on to EPFL in Switzerland, where they implemented some of the stuff, it actually generalizes quite nicely. So even though this is a very simple system I'm talking here, it actually applies very nicely to complicated robots. Real robots do this. So this is the dynamics of the lip. So basically it is just this pogo stick in some sense, except that you constrain the top of the pendulum, if you like, to move around in the plane. And then you want to generalize it to a lip biped, which again is basically the same thing. You have the mass moving in the plane, and you have two legs as opposed to the one leg. So that's the model that I'm talking about. So that's the schematic of the leg. It's this telescopic leg. You have actuator constraints. The motion is constrained to the plane, and you'd like to look at its motion. So that's the idea. So you can develop the equations of motion. Again, it's very simple equations. It looks a little bit like the rigid body equations I showed you earlier. You can look, if h is the total angular momentum of the point mass, like in the rigid body equations, you can check the equations take this form here, dh by dt equals mr cross h. You can solve explicitly for h, and you combine the equations to get the equation that I wrote at the bottom here. The details don't matter too much. The idea is then we want to look at the symmetries that arise from these equations. So we go to a nice Cartesian coordinate system, and you apply the constraint that the mass should move in a plane above the surface where you're walking. There's a constraint, x squared plus y squared plus z squared is equal to a constant. And if you put all that in with z equal to z0, you get these equations here, which basically just look like two harmonic oscillator equations again. X double dot equals omega squared x, and y double dot equals omega squared y. And you're just using some sort of actuation to keep those in place. So you're using the sort of nonlinear dynamics to give you this, in some sense, simple linear dynamics. And these are the equations of the lip. And you can of course, they're simple equations, but in order to enforce it, you need an actuator force. You can compute what sort of actuator force you need to enforce the horizontality constraint that I just mentioned. And the idea is to think of somehow as this, as a simple model of walking. You want a pattern generator for walking and a controller which enforces this horizontality constraint. So as I said, of course, this is a monoped. It can't really walk. You can generalize it in a natural way to a biped, which has legged locomotion. And basically what you're doing is you're just taking the monoped and enforcing the symmetry so these legs switch back and forth in a nice way. And that's sort of the key to what we wanted to do here. As I said, really, it's just the set of equations. If you want to generalize it to a biped, you have a transition map, which corresponds in mathematically to hitting this Poincare surface. On the transition map, you have the legs sort of swapped instantaneously, so only one leg is the stance leg at a time. And during the switching of the legs, the mass remains on the plane, z is equal to 0, and z dot is equal to 0. So that's the very simple model of walking here. But as I said, it's enough to illustrate what we do here. And again, just sort of mathematically and to connect with what I want to say later, you can think of it as Dan likes to do, you have a continuous phase and a discrete phase. The continuous phase is just these two simple harmonic oscillator equations, and then there's a discrete phase where one of the legs hits the ground and you have a swap. So those are the equations of motion, the simple harmonic oscillator equations coupled with a transition map. And yeah, so just in the analysis, actually, it doesn't really matter too much here. In order to do the analysis, you need to choose a suitable coordinate frame. And the idea is that the nice coordinate frame to introduce here is one with a Cartesian coordinate system, which sort of is associated with whichever leg is in action. So either the stance leg or the other leg. So the details don't matter too much, but it slightly affects the equations of motion that you get here. Okay, so yeah, so again, that's related to the choice of coordinates. We say the lip is invariant if the set of conditions hold here. And you can show that under these conditions, we have what's called an x naught y invariant 3D lip, which is the model that I'm looking at. So the question is basically, how do you get a nice, stable locomotive gait for the system? And this is where we introduce this notion of symmetric hybrid systems. So this, as I said, is an example of a larger class of systems, which we call a symmetric hybrid system. And I just want to say briefly what's that about. But the important thing is that a symmetric hybrid system can have a set of infinitely many periodic orbits. you can look at the linearized Poincare map to see how the stability works, and you can show, in fact, that these orbits are asymptotically stable and provide nice locomotion. And in fact, the 3D lip is an example of this. So the key idea here is the notion of what's called a symmetric vector field, and so the lip is exactly that example, and the idea is to choose a system which has a symmetric vector field and to impose a suitable transition map on that system. So what is a symmetric vector field? So I have a smooth vector field on X. It's symmetric if you simply have, so the vector field is X, that's the dynamics. I compose it with some map called G, and you can, if X of G is equal to GG of X, it's said to be a symmetric vector field. And so that basically, so this is just comparing if you move around in the configuration space, you make some sort of transformation, that's equal to dg of x, where dg affects the vector field. So I'll illustrate this in a moment. And the idea is if you have x of t, a symmetric vector field passing through a fixed point at x equal to 0, then x of minus t is equal to g of x of t. So that's the symmetry. So there's a symmetry in the configuration space, and it basically leads to a vector field which is sort of symmetric in time. So if I replace t by minus t, that's equal to g of x of t, and we say that's a symmetric solution of the symmetric vector field. And you can add in impacts as well, so you can add in symmetric impacts. And again, if we have a feasible solution of a symmetric hybrid system which crosses the switching surface at time t, you can show that the solution is periodic with time 2t. And I'll illustrate that in a moment. So the whole point is if you have a symmetric system with a symmetric switching surface, you generate a periodic orbit. And that's basically the key to the whole thing. So this is really the idea. It's a very simple idea in some sense. So this is the sort of more general map. We have a Q-dimensional manifold. Q is the configuration space. You have S, a one-dimensional submanifold of TQ, the tangent space, and which is basically the switching surface. So, and this is basically the definition of this K-dimensional second-order hybrid system. So it's basically second-order dynamics, like the dynamics I had for the lip. I have a switching surface, and what I'd like to do is have a symmetric vector field which sort of respects the sort of conditions that I just showed you. And as I said, the lip is exactly such an example. It's a two-dimensional second-order hybrid system. And basically the idea is you have some sort of switching surface. That's the switching surface S. I have some sort of orbit as the system goes through the switching surface. And the idea is what I want to do is make it periodic. And so let me just sort of describe it intuitively somehow. Right, so if I have an orbit of the system, right, it may or may not be periodic, right? It'll hit the Poincare surface, and it may or may not return back to the same point. What you want to do is make sure that the vector field is such, by imposing certain symmetries, that you hit the same point again, and that it's periodic. And that's sort of basically the key idea here. So, so this is the definition of the system. It's a generalization of what I just showed you. I have a smooth K-dimensional second-order hybrid system, and I have all these invariance conditions that I just showed you earlier. It's invariance to the impact map. I have symmetry in the vector field, which corresponds to f being an odd function. I have symmetry in the impact map, and the whole, if I put the whole thing together, I get the so-called symmetric vector field. And and you can check that all these conditions that I just showed you are satisfied for the smooth dynamics and the impact dynamics of the lip. And let me just show you. So this is the lip, and let me just show you a picture of the dynamics. So basically, the idea is the following. So if I just think of it, so if the lip is in x and y space, if I think of the dynamics in x and y space, I get some sort of curve. If you look at the red curve here, that's sort of what we call an asynchronized or non-symmetric system. It doesn't return symmetrically to a point that I want. But basically, what we do is if we impose these symmetry conditions that I just gave you, that'll give you this blue curve, the second curve here. And the idea is basically, if you can think of, say, the periodicity or half the periodicity of the orbit in this picture, you basically move from the left-hand point to the right-hand point. If these things are nicely balanced among each other, when I get to that point, I can just take the impact map and return myself from the end point on the right to the beginning point. and that gives me a periodic orbit. So basically, I move in a symmetric way in xy space. When I arrive at the end point of that motion, that's the impact map. I have a symmetric impact map that returns me back. So if it takes me time t to get from one point here to the other, I get a periodic orbit of time 2t. And that's basically the idea. So, so the idea is if I have a, so the proposition basically is if I have a symmetric hybrid system with a symmetric coordinate system, it has infinitely many synchronized solutions, 5t psi t, where 5t is odd and psi t is even, where t equals 0 corresponds to the mid-step. What you can show is this gives rise to this periodic behavior. So, so the idea is, you know, so if you want to think about this picture again, the idea is, you know, it has a particular shape here. If you think of that 0 as the midpoint, this could have different kinds of shapes. So every time I pass through the midpoint, I can have a kind of symmetry of the system, and I get the stable locomotion. So that, it's very simple, but basically, that's how it works. So those are the symmetric hybrid systems, and I say it applies to the lip, but you can apply it quite generally to more complicated systems. So I want to sort of, so now I'd like to sort of come back. So I'd like to relate these two things. I'd like to look at non-holonomic systems with impacts. So we just looked at this simple, so we looked at the rolling penny earlier. We looked at the Chaplagan sleigh. We looked at the lip. As I said, you could, so now you could try and combine them. Suppose I had a real system, say a rolling system or a rolling ball with impacts, and I'd like to look at the dynamics. So it turns out this is actually a very nice problem. As I said, a classical mathematical problem is you simply have a particle which bounces across some sort of enclosed surface. But you can think of, say, the rolling penny, putting it inside some enclosed surface and looking at the dynamics. So this is what I want to do. So I want to think of my rolling penny, so you can think of it as perhaps you could generalize it to a tire or something like that. You can break it up into elastic impacts or plastic impacts. So if elastic, it sort of bounces off without losing energy. Plastic, it loses energy. And you get some sort of projection which sort of captures the dynamics. But in any case, you can write down the dynamics in this case. So again, it's pretty much what I wrote earlier. You can write down the Lagrangian for the non-holonomic system, which describes the rotation of the system. Plus, you have some sort of impact conditions, right? Either on the Lagrangian or on the Hamiltonian. And if the impact time is free, i.e. delta t is not equal to 0, you get conservation of energy of the impacts. And you can have impacts actually which either preserve energy or don't preserve energy. But in any case, you get two sets of equations. So basically, you get the dynamics, which corresponds to the non-holonomic equation that I described earlier. Plus, you get the impact condition as well. So you can impose this impact condition onto the non-holonomic dynamics. So here, L is just the Lagrangian. Omega k imposes the constraints. H is the impact map. And you end up with a sort of non-holonomic system with impacts. And it turns out to have rather beautiful dynamics, which I want to show you in a moment. So, so that was the elastic case. You can do the plastic case as well. I'll omit the details, I think, for reasons of time here. But you can write down the non-holonomic impact map, which just encodes how much energy is lost when you have impact. But we can actually apply it again to this, as I said, to various examples, but in particular to the vertical disk. To go back to my disk, which you saw earlier, this is the Lagrangian for the disk. And I can think about my disk as sort of moving around and impacting some sort of surface at a given time, and you want to see what happens. So it's going to bounce around and do interesting things. So again, the dynamics I sort of showed you more or less earlier. I have the rolling constraints without slipping. These are the dynamics of the disk, and I just impose the constraints. And this is what it looks like, basically. You have the constraint equations. This is the impact map, which is a little bit complicated because I'm just looking here, for example, either at a given plastic or elastic impact. The details don't matter there too much, but you can write down the impact map quite explicitly, which I've done here, just as for the non-holonomic constraints. And let me just show you the numerical results. So we've tried it on various cases. So what we thought of is either a circular, you can take a circular table, or an elliptical table. These are the classical things that people look at. And I've just shown you here the circular case. So what happens, again, for periodic behavior, so you get this rather beautiful dynamic. So this is the circular table, and this is the elliptic table. So this is the rolling penny. So if I just started off, for example, say in the center and started rolling it towards the edge of the circle, it sort of moves in a nice smooth way, it bounces off, and then it moves back into the center and so on. And you get this beautiful sort of periodic motion. It looks like sort of the leaves of a flower, for example. So that's the circular table, which I think in some sense, it's like an integrable discrete system. It's got this rather beautiful periodic behavior. And this is the elliptic table, which is rather more complicated. So this is numerical simulations, by the way. So this is something we've just done. So I think this is stable, integrable periodic motion. I don't know that. This obviously might even be chaotic. But in any case, you get this rather beautiful dynamics. So just in the remaining time, how am I doing on time here? 5 minutes, maybe? Yeah, so that's the dynamics. So let me just mention a couple of other things. So one of the other things that we've also just started looking at recently, one of the problems, as I understand in robotics, is if you have foot slip. So suppose that, going back to the pogo thing, as opposed to impact on the table, you had the stick or the biped could actually have foot slip. You also end up with rather beautiful dynamics. So this is combining what we had earlier. You have a sort of free dynamical system. It impacts. When it impacts, there's a little bit of slippage. And the model that I'm looking at, so I won't worry too much about the details since I need to end it up, but basically what I've done is I've just taken that pogo stick-like object here, and I'm impacting on some sort of surface which has an angle with the horizontal, and this guy can slip. And we again do the same thing. We look at a linearized Poincare map to capture the stability of the periodic orbits. And let me just show you those. So I'll skip. The dynamics is very similar to what I just showed you, but let me just show the pictures, as we're running out of time here. So we compute the dynamics on the Poincare section, and you end up with this rather beautiful dynamics. So just go to that. So this is actually a picture of the dynamics. So this is just the Poincare surface, if you like, and you end up with this rather beautiful surface with these tongues, actually. So you end up with a surface which looks basically like some sort of perturbation of an integrable Hamiltonian system, but it has this rather rich dynamics which we're studying right now. So this is basically the Poincare section of this biped interacting with a surface with a kind of slope and with possible slippages you hit as well. So again, the nice thing about it is we can compute it explicitly, at least numerically. You get this very rich looking dynamics, and we're still sort of analyzing that, trying to look at the stability of the periodic map, seeing what sort of instability you can get. So the last thing I want to mention, so I don't have too much time to talk about this. We've also been looking some recently at periodic orbits in biological systems, and they're two sort of, again, so the idea again is that I have a low-dimensional dynamical system, I have some sort of symmetry, and you want to know about the existence of periodic orbits. And let me just sort of end by showing you a couple of these. So this is related not to some work on robotics I've been doing, but we were looking at some work people doing, as I mentioned earlier, sort of mathematical biology, control of cells, actually. And one of the standard things that people do there is build these synthetic biological models. And one of them is the so-called repressolator, which you can think of basically as 3 particles arrayed on a circle. And so so it looks like, so x dot equals to minus x, there's a simple dissipation, and the next particle, say the y particle, influences the x particle with some sort of repressive term. So x dot equal to mu of 1 plus y to the n minus x. So you can think of these 3 particles, they're arrayed on the circle, and the symmetry here, basically, is there's a cyclic symmetry. So these equations are exactly cyclic in the sense if I change x to y, I get the next equation, then I change y to z, I get the other one, and so on. There's a beautiful cyclic symmetry, and these equations also have beautiful periodic behavior. So that's the repressolator. It exhibits stable periodic orbits. So here's another example that I looked at with Matt Kvalheim, who's in the audience here. So again, there's a nice symmetry here. It's just quadratic, linear, and some sort of dissipative term. And again, it's sort of related to these various biological systems. And again, it exhibits sort of beautiful periodic behavior. And let me just sort of end by showing you a couple of pictures. So it's an example of a large class of systems, but this is basically what you get. So this is basically a picture of the Sprott system with no damping. You can see that there are these three oscillators that sort of oscillate in this beautiful way. And I should say, by the way, that it's really hard to prove this periodic behavior. So one of the interesting things is, you know, for these robotic systems, we're sort of imposing the periodic behavior in some sense. It's still tough to prove stability, as many of you know. On the other hand, for these biological systems, even showing the existence of periodic orbits is really tough, actually. It's tough for the oscillator. It's even harder for the Sprott. But nonetheless, with some work with Matt, we were able to do this. For higher dimensional systems, proving stability, it's really tough. You know, there's a picture. Let me just, so there's another picture if you have no damping. That was with damping. And here's another rather beautiful picture of the oscillator in X, Y, and Z space, which Matt generated. You can see you get these rather beautiful trajectories, and you can prove they are periodic, and we think stable, but I think that's still open, as far as I know. Yeah. Okay, so I'll stop there. Thank you.
I think we have time for maybe one question. Go ahead, Matt.
I was wondering, have you guys thought about, for the case of the billiards with the rolling pennies, I guess the first question is, how would you compare and contrast the behavior with classical billiards where you have a particle bouncing around?
Yeah.
And the follow-up question is, have you thought about, if I shrink the radius of the penny or something, is there some way to obtain classical billiards in the limit?
Yeah, that's a good question. So we have thought about that. I don't know the answer to that. So you do get sort of different trajectories. So for the particle, for example, right? You can so the trajectory sort of it's kind of for the circular case, it kind of mimics fairly closely the particle, I think, but you get the rolling behavior. I don't know about the elliptical table. So the idea is, I guess, the mantra in the billiard case is, depending on the shape of the table, you either get periodic, you either get integrable behavior or non-integrable behavior, and that's what we're trying to show in this case. So we think, say, for the penny, with sufficient symmetry in the table, you get an integrable non-holonomic system. I'm pretty sure that is. The elliptic case, we think it's chaotic. And I think that's true also for the particle as well. But we're not quite sure yet of the exact analogy between the two. But that's exactly the question if we're trying to look at. And there are other interesting tables as well. People look at octagonal tables. There are all sorts of interesting tables that give rise to interesting dynamics. So we're still looking at that. And we also want to look at the actual billiard ball as well. And then, of course, you can add in things like slipping anyway, all sorts of things. Yeah.
There will be time to talk to Tony over lunch, over the pizza lunch, which I encourage you to do. Beseech him with your problems so you can get him to work on idealized versions of your problems. And that would be amazing. Thank you so much.
All right. Thank you.